let us now come to the third part of the presentation in fuels and combustion. Okay, so this is now the typical combustion reaction. Okay, so basically, fuel needs air in order for the fuel to ignite. Okay, so fuel plus air is equals to the product of combustion. Okay, so here is now the basic balanced equation, okay, or the balanced equation of hydrocarbon fuel. So if we look at now the equation that is C, meaning carbon and hydrogen. So the N and M here represents the number of moles of carbon and oxygen. So plus, that is N plus 0.25 of M. So this is again the number of moles of carbon and nitrogen multiplied by oxygen plus 3.76 multiplied by N plus 0.25 M multiplied by nitrogen. So in this air is composed of oxygen and nitrogen. So that is why we have here oxygen and nitrogen. And that yields also to NCO2. So meaning the number of CO2 and the product of combustion. Okay? So and then the product or the amount of water vapor and the product of combustion. And another is the nitrogen, since nitrogen is not combustible. Okay, so whatever nitrogen rather comes in will equal to the amount of nitrogen that goes out. Okay, so here is now the theoretical air fuel ratio. Okay, so theoretical air fuel ratio, of course, that is the amount of air divided by the amount of fuel. So air here is the so-called reactants. Okay, so that is now the numerator here, and determining the theoretical air fuel ratio divided by the fuel. Okay, so the derived equation for that, if the chemical formula of fuel is known, is equal to 137.28 multiplied by the number of moles of carbon plus 0.25 number of moles of hydrogen divided by 12 carbon plus the number of moles of hydrogen. Okay, so this is now the derived equation. But if you do not know, or if you forget this kind of equation, you can also balance the equation of the hydrocarbon fuel. So by just putting out or putting the hydrocarbon fuel plus oxygen plus nitrogen, since the nitrogen is 3.76 times the oxygen, and the composition of air plus CO2, H2O, and hydrogen. And then assigning designating variables to oxygen, hydrogen, or not hydrogen rather, but CO2 and H2O, and then balancing the carbon at the left side and at the right side, and then you will obtain also the same balanced equation to this. Okay? So let us now proceed to the classification of combustion reaction. Okay? So one is the combustion reaction with chemically correct or stoichiometric condition. General chemical formula of the fuels is CnHm. Take note, when we say stoichiometric, meaning we are referring to theoretical condition. Okay? So, another is the combustion reaction with greater amount of air. Okay? Theoretical air. Or having a fuel-in mixture. Meaning we are putting an amount of air or we are supercharging. Okay? So, we are putting an excess air. So, another is combustion reaction with lesser amount of theoretical air. Meaning, the amount of air needed is below the stoichiometric air needed. Okay? Or the theoretical air needed. Okay? So, I think it is clear. Another is we have the equivalence ratio or a given mass of air. Okay? So, we have here the weight of the theoretical air and the weight of the actual air. So, this is equivalence ratio. So, if you get the value of the theoretical air and then the actual air, get the ratio of that, that is called the equivalence ratio. Okay? So, this equals to 1 for stoichiometric mixture, less than 1 for fuel-in mixture, and greater than 1 for fuel-rich mixture. Okay? So, another is ORSAT analyzer. So, is a convenient portable apparatus for determining the volumetric percentage of carbon or yes, CO2, oxygen, and CO or the carbon monoxide in the dry flue gas. Okay? So, for the dry flue gas or from actual combustion, so we have here the weight of the dry gas. So, that is 4 multiplied by the carbon dioxide and the product of combustion plus oxygen plus 700 over 3 multiplied by CO2 or the carbon dioxide and the product of combustion plus CO multiplied by the carbon actually burned. Okay? So, CAB. So, boiler test code formula corrected to account for the sulfur dioxide. Okay? So, because in the previous equation above, sulfur dioxide is not included. So, it is impossible for a product of combustion without sulfur content or sulfur dioxide content. Okay? So, to determine now the weight of the dry gas, so that is 11 CO2 plus 8 O2 plus 7 multiplied by the quantity CO plus N2 over 3 plus CO2 plus CO multiplied by the carbon actually burned plus 3 over 8 over sulfur. So, this sulfur now is included plus 5 over 8 of sulfur. Okay? So, where CO2, O2, and CO and N2 are volumetric ORSAT analysis. Okay? So, the carbon actually burned and S are, of course, so they are all in decimal fractions, okay? Or in decimal, okay? So, another is the weight of the dry refuse, okay? So, meaning we are not assuming that all the fuels fed to the furnace are burned 100%. Okay, there is, of course, a refuse. Okay, so the weight of refuse, of course, that is us divided by 1 minus combustible refuse. Okay, or combustible in refuse. Okay, so the carbon actually burned, of course, CAB is equals to the amount of carbon minus the weight of refuse plus us. Okay? So, that is Carbon actually burned is equals to C over the weight of dry refuse multiplied by the heating value over 14,600. Okay? So, another is carbon burned to carbon monoxide due to incomplete combustion. Okay? So, we have here the carbon burned is equals to CO divided by CO2 plus CO multiplied by carbon actually burned. Okay? So, it is imperative class that the formulas involved in combustion is very important. Okay? Another is the air actually used during combustion. So, air actually used. So, that is equals to weight of the dry gas plus 8 multiplied by H2 minus O2 over 8 minus carbon actually burned minus sulfur minus nitrogen. Okay? So, very sufficient to complicated formulas. Okay? Okay, class. Let us now take an example. A manufacturing company in Metro Manila operates a diesel electric plant to supply its electric energy requirements. During a 24-hour period, the plant consumed 250 gallons of fuel at 80 degrees Fahrenheit and produced 2,700 kilowatt hours. Okay? Industrial fuel oil used is 30 degree API and was purchased at 3 pesos per liter at 60 degrees Fahrenheit. Determine the overall efficiency of the plant. Okay? So, the definition now, solution. Definition of the thermal efficiency or overall efficiency equals to output, of course, divided by the input. So, we have here the energy output. So, in 24 hours, that is 2,700 divided 24. So, because the plant operates 24 hours a day. Divided by, of course, the energy chargeable, which is equals to mass of fuel consumed multiplied by the heating value. Okay? So, take note, the mass of fuel consumed here is the fuel consumed per hour. Okay? So, getting now the heating value in terms of degree API, heating value is 45,318 kilojoules per kilogram. Okay, solving now for M. Okay? So, specific gravity. So, that is equals to 141.5 over 30 plus 131.5. The specific gravity at 15.6 now is equals to, or 60 degrees Fahrenheit, is 0.876. So, and the specific gravity at temperature T, or at 80, that is equals to specific gravity at 15.6 or 60 degrees multiplied by the factor 1 minus 0.0007 multiplied by 26.67 minus 15. So, 26.67 is in degrees Celsius equivalent to 80 degree Fahrenheit. So, therefore, the specific gravity now of the fuel at 80 degrees Fahrenheit or 26.67 degrees is 0.869. Okay? So, from the definition that density equals to mass over the volume, and then getting mass now, that is equals to 0.869 multiplied by 1,000 kilogram per cubic meter. So, the consumed mass is 250 per 24 hours. And then, converting cubic meter to gallons, and then hour to seconds, the equivalent now is 0.0095 kilogram per second. So, changing now the mass from the formula for efficiency, substituting values, the thermal efficiency now is overall is 26.08%. Okay? Another example, class. So, a certain coal has the following ultimate analysis. Ash is equals to 5%, carbon is 70%, hydrogen is 20, 2.5% rather. Moisture is 10%, nitrogen is 4%, and sulfur is 5%. Or oxygen is 3.5%. Okay? So find the actual air fuel for an excess air of 30%. Okay, class, so this is very easy. Air fuel ratio theoretical. So this is 11.44, or sometimes you will see an equation using 11.5. Okay? Carbon plus 34.5, hydrogen minus oxygen over 8 plus 4.29 or 4.3 sulfur. Substituting values, the amount of the theoretical air now is equals to 8.977 kilogram air per kilogram of fuel. Ibig sabihin, or for every kilogram of fuel, it requires 8.977 kilogram of air. Okay? So, for excess air of 30, so just multiply the theoretical air by 1.3 since excess air is 30%. So, therefore, the air fuel ratio actual now is equals to 11.671 kilogram of air per kilogram of coal. Okay? So, very clear class. Okay? So, very easy. Thank you very much. So, that ends my presentation, class. So, wait for another presentation here. So, we will solve another examples in order for us to be clear with the formulas and application of combustion or fuels and combustion. Thank you very much, class.